So let's construct our first strong seeded extractor under some restriction on the form of the side information. So in fact, we're going to consider the same scenario that we considered in the previous example. So we take a source x, which is an n-bit string, and we assume that the side information e consists of p times n of the bits of x. We don't know which bits, but we know that it's p times n fixed bits. In particular, under this condition, you can evaluate the min entropy of x conditioned on e, and you can see that in this case, it's going to be 1 minus p times n. So that's the number of free bits that we have left. Our goal is to come up with a procedure that extracts as many as possible of these bits. We're going to manage to extract essentially all of them. So I recalled the definition of a strong seeded extractor for you over there on the top right. And we'll use the same construction as we used before. So the seed is going to be pretty long. It's going to have seed length d, which is n times m, where m is our target output length. So we'll see what we get a little bit later. And we'll interpret this seed of nm uniform bits as m bit strings. Each of them is made of n bits. So y1 has n bits, ym has n bits, and the extractor on input the source and the seed will output m bits obtained by taking the inner product of the source x with the first part of the seed y1, and then the inner product of the source with the second part of the seed y2, etc. up to the mth bit. Our goal is to show that as long as m is not too large, then this is uniformly distributed, conditioned on both the side information and the seed y, because we want to show that this is a strong extractor. So here's one way to argue about this. We can think of what this procedure is doing as matrix multiplication over the binary field. How do we see this? Well, let's consider matrix A, which is simply the matrix whose rows are given by the y's. So it's a matrix that's pretty long like this, and the first row is y1, second row is y2, etc. up to ym. Now I can think of x as a column vector of n bits, and z as the product of a times x, right? In the first entry here, you'll have x.y1, in the second you'll have x.y2, if you consider this matrix vector product over the binary field. So now we want to argue that this is uniform. Okay, so what is it about x? The side information contains p of the bits of x. These p bits, they're at certain locations here, and these are fixed. So when you do the matrix vector multiplication, the fixed bits, you can draw them in blue, these will correspond to taking fixed columns of this matrix. So these are columns that are always either taken if the bit is a 1 or not taken if a bit is a 0 when we compute this dot product. Now the other columns are each chosen uniformly at random depending on the value of x in these coordinates. Now what you can see is that as long as the span of the non-fixed columns, as long as this has dimension at least the dimension of the output, m, so let me write it like this, dim of the span of the non-fixed columns is at least m, then the output is going to be uniformly distributed. Because if the span of these columns is m, the dimension is m, it's the whole space, and now I'm taking a random linear combination of the non-fixed columns. If they span the whole space, I'm going to end up with a uniformly random vector. So as long as this is the case, I'm safe. And when is this going to be the case? Well, if the number of non-fixed columns, which is 1 minus p times n, is greater than m, let's say much greater for safety, because we're choosing these columns at random, it could always be the case that all these y's are chosen to be zeros, and then of course we'd have a problem. But with high probability, if we think of, instead of choosing y by rows, we choose it by columns, as long as the number of columns that are not fixed by the eavesdropper side information, which is 1 minus p times n, is much larger than m, then the dimension, they will span the whole space, and so we'll get a uniformly random output. Even if the matrix y is known. So note that here the argument doesn't require y to be unknown. What is important is that which bits are fixed, meaning the adversary's side information. This is determined before the matrix Y is chosen. Otherwise, we could always tweak things. But here, the eavesdropper has to fix certain bits of X, it gets to know them, then we choose a random matrix Y, and with high probability, as long as the number of output bits M is less than the number of free bits 1 minus P times N, we're going to select a matrix whose free columns, which we don't know what they are, but they're there, they're set, the eavesdropper has decided which bits to keep. So the span of these free columns will be the whole space. And once that is the case, even if we tell the eavesdropper what the matrix is, then it's just going to realize that it didn't keep the right positions. There's too much freedom in the positions on which it has no information, and so the output Z is going to look uniformly random from the point of view of the eavesdropper. So this extractor is a strong seeded extractor. It works well. It has one drawback, which is that the seed is very long, n times n uniform bits. If we think of the setting of parameters that was outlined in the previous module, m is kind of the same size of n, so this is a quadratic number of bits. It's a lot. So what we'll achieve a little later is that we'll bring this down to a constant times n instead of n times m. This will be called extractors based on 2 universal hashing, and we're going to learn about these in the next module.